Hello everybody, and welcome back to Lesson 23 of the Dead Earth game development series, brought to you by none other than the Game Institute. In this lesson, we are going to create the pursuit state for our AI zombie state machine. The pursuit state is the state that any of our other states will transition into when our zombie has ascertained the source of a threat. So in the case of a visual threat such as the player, this means that when the zombie has a line of sight of that threat. In the case of an audio source, it's when the zombie has been able to figure out where that sound source is coming from. But either way, the result is the same. The zombie is going to go into a mode that is going to have it getting to that target location with haste. So in the case of our patrol state, for example, where we have a speed of 2, which in our animator is our zombie jog animation, in the pursuit state we'll set it to a speed of 3 so that our zombie sprint animation is played instead. And that'll look really cool because you'll have the zombie doing a kind of leisurely jog running around our level, and then all of a sudden it sees something that it considers a threat and it will just go into a sprint and come running straight at us. Now the pursuit state is also going to work very much like the patrol state. We're not going to be using any route rotation to turn our character because, well, we don't have any in our animation tree. So what we'll be doing, like I said, like the patrol state, is we will be rotating Jill on the spot while she's in a pursuit state to try and keep her aligned with our steering target. Okay then, so one of the things that our pursuit state is going to need to know is when it's going to be close enough to the player such that it can transition into the attack state. It's going to need to know when it's close enough such that it can then play the animations that will have it clawing, scratching and biting the player. We don't want the zombie going into these animations too far out from the player, or otherwise the clawing and the scratching and the biting just won't reach the player. And we're going to do that using a special type of trigger called a melee trigger. And in order to facilitate the melee trigger system, we're going to need to also set some stuff up in our base state machine class. So let me try and explain how this is going to work. So I'm going to add a capsule to the scene, which we can pretend for the time being is the character controller of our character. Okay, so let's imagine that this is our character construct, and on top of this capsule here we have maybe our first person camera. Okay, so we need to know when the zombie is close enough that it can perform animations that will have its hands or its biting routines passing through and intersecting our actual character collider. So the way we're going to do that is by having a secondary child object on our character controller called a melee trigger, and I will simulate this by adding a sphere as a child object to this capsule. Okay then, so this game object, currently called sphere, is going to be our melee trigger, and it's going to be a trigger, so I'll just temporarily tick the is trigger box just so there's no confusion. And it will also be on the AI entity trigger layer. Remember, this is the layer that our target trigger is also on for our zombie, something that is sensitive to the zombie's actual body collider, this capsule here, entering it. So in other words, if we have a script on this trigger here, then when zombie Jill enters it, it's going to get notified using Unity's usual methods: on trigger enter, on trigger exit, on trigger stay, etc. So what that melee trigger script is going to do on this sphere is when it detects that the zombie has entered it, it's going to contact that zombie's state machine, and it's going to say to the zombie, "You are now within my melee range." And the zombie state machine is going to have a Boolean value called in melee range, or something like that. And when that's set to true, well then our pursuit state will know that it can now transition into the attack state, and then it can then start playing some attack animations. And of course we'll have to play around with the size of our melee trigger to get something that makes sense with the reach of the zombie's melee animations. It works pretty well. So if we imagine this is our character moving around the level, okay, minding his own business, and imagine Jill is running at us in her pursuit state. It knows at the moment that it's not within melee range, but as it becomes closer to our character, Jill's collider is going to intersect our melee trigger, and the script on our melee trigger is going to contact Jill's AI state machine, and it's going to say, "You are now within melee range." And then Jill is going to know to transition into the attack state. And of course, when the zombie is no longer in the melee trigger is going to get notified by Unity by means of an on trigger exit function, and then it can contact the zombie again and say, "Hey, you're no longer in melee range." So our state machine is going to just need to have a Boolean that is going to let any state know whether the zombie is close enough to the character to go into an attack state. So what we'll do first of all is we will open up our AI State Machine base class and we will add that in melee range Boolean property. So remember, our AI scripts are in our Dead Earth folder, the script subfolder, and the AI subfolder. If I open it up in MonoDevelop, there is our AI State Machine class, and I'm going to just go all the way down to the properties section, and I'm just going to add in there an automatic property called in melee range of type Boolean, and it has a getter and a setter. And it needs to, because our melee trigger script is going to need to be able to set this when it detects the zombie has entered the melee trigger. And it needs a getter because our individual AI states are going to want to query this value. And if it finds, for example, in the pursuit state that this value is set to true, well, then it's going to transition into the attack state. So let me save that off. Go back to the editor, and what we'll do now is we will create our pursuit state. So I'm going to create a new C# script in our AI scripts folder, and I'm going to call this AI zombie state underscore pursuit 1, like so. I'm then going to open it up in MonoDevelop, and of course we're going to, as we always do, delete the boilerplate code, and of course change the base class from mono behavior to AI zombie state, like so. And we're now ready to start adding code to our new AI zombie state pursuit class. So because we have quite a lot of stuff to get through in this lesson, I'm going to pick up the pace a little bit when showing you the code to this state, because most of the stuff here is much like the code you've seen in other states. There's nothing really new. So the first thing we have to do is we have to think about the variables that we're going to need. Well, as with our patrol state, we're going to want a speed variable that we can use to tell the animator which animation we would like to trigger. Like I said, I'm probably going to set this to 3, but we'll make it an inspector assigned variable anyway. So it's something that we can change within the editor. So I'll make this a serialized field with that range attribute so we get a nice slider bar, and it's a private float called speed, and I'll set it to 1 by default. But like I said, in the inspector I'll set this to 3. Now, because we're going to be rotating our zombie Jill on the spot, much like we do in the patrol state, then just like the patrol state, we're also going to want control over the slurp speed, the speed at which we rotate from our current orientation onto our ideal orientation where we are facing our steering target. So as with the patrol state, I will make this a serialized field so we can change it in the inspector. It's a private float again, and it's called slurp speed. So something that we're going to have to deal with in this state that we haven't had to deal with in other states is the fact that when we're pursuing a target, the target may be moving. Think of the player, for example. Therefore, we can't simply generate a path in the onEnterState function and leave it set for the remainder of this state's lifetime. No. While this state is active, we're going to have to periodically recalculate that path to the target's new position. Because repathing can be quite expensive, we certainly don't want to be doing it every single frame. And furthermore, we probably want to do it less for threats that are further from the zombie. As the zombie gets closer to the target, we want its repathing to become more frequent so that it's more accurate. So what I'm going to do is I'm going to create a repath distance multiplier. Okay, as you can see, it's another serialized field, and it's a private float, and I call it repath distance multiplier. And what we're going to do with this variable is we're going to use this to scale the distance between the target and our zombie, and this will essentially be setting the number of seconds, or the fraction of a second, until the next repath should be done. Now, I found through trial and error that having a repath distance multiplier of about 0.035 is a pretty good starting point. It basically means that if the target is around 20 meters away from us, well, then we're going to be recalculating a new path every 0.7 seconds. Obviously, as the distance increases, that becomes less. And as the distance draws closer, then we want to recalculate that path more frequently, but probably still not every single frame. So what we're also going to do is create a min and max value for dealing with visual threats in this way. I call this repath visual min duration and repath visual max duration. What we're basically saying is however close the zombie is to the target, we never want to repath more than 20 times per second. That's 1 over 0.05. That should be plenty of accuracy for approaching a moving target, even when we're in quite close proximity. Because remember, in the case of a player, which is a visual threat, once we get within a certain range, we're going to enter the melee trigger and we're going to be put into an attack state anyway. And in the attack state, we are literally just kind of gluing the zombie to the player, but we'll discuss that in another lesson. So I'm basically saying that we're going to have a timer, and every time we recalculate the path, we're going to set that timer back to 0 again, and another path will not be calculated until the timer is incremented past whatever the distance to the target is multiplied by 0.035. But we will never calculate it at a frequency of more than 0.05 seconds, and we will never calculate it less than once every 5 seconds. Now, we're probably never going to get to the once every 5 seconds scenario, because once it's so far away from the target, it's probably not even going to be in pursuit state anymore. But it's good. It allows us to essentially have AI LOD, or certainly pathfinding LOD. But of course, a visual target is generally a moving target, and an audio target often isn't. So what we'll do is we'll have a different repath min and max for audio threats. We want it to be more accurate for the player, but for any of his other senses, such as the audio, at the most we only calculate a new path every quarter of a second. So of course, because we need to keep track of time, we're also going to need a private internal timer variable. So I create a private float called timer, which is set to 0 by default. Now of course, we're also going to need to keep track of when our zombie has reached its target, so that in the case of the player, for example, we can transition into the attack state. But in the case of an audio source, if we imagine that just a sound was made and the zombie went to investigate it, then when the zombie reaches that target, we probably just want to say the target's been reached, let's just drop back into the alert mode and just stay looking alert for a few seconds until our alert default duration has expired, and then maybe that zombie would resume its path again. Remember, with something like a sound threat, it's really just a case of getting the zombie to that location, and then if he drops back into the alerted state, starts rotating left, starts rotating right, there's a good chance that the visual threat that caused that audio might actually come into the view cone and trigger the zombie into pursuit mode. So I'm going to create a private boolean called target reach with an underscore, which is set to false by default, and of course we're going to know when the target's been reached, because when the zombie enters the target trigger, the parent state machine is going to call this state's on destination reached function, and we can use that to set this target reached to true or false based on whether we've reached the target or not. So the first function we'll create is that one that we've had to create in all of our child states, which is the one that is called by our parent state machine to retrieve the type of state this is. So as you can see, our get state type function is the same as in all our other states, only this time it returns AI state type pursuit. And like I said just now, we're also going to want to keep track of when we've arrived at our target, so we will also override that function from the base class on destination reached. Just to remind you, this is called by our parent state machine whenever we enter our target trigger, and it's passed a boolean whether we've arrived at the target or not. And we simply set this boolean to our target reached variable so that our update function will be able to react to that. So let's now create our on enter state function where we set this state up ready for being the focus state. We will put a debug log in there that just lets us know we are entering the pursuit state, and we will do that same logic that we've done in all of our other on enter state functions. We call the base class on enter state method, and then we check that we have a valid zombie state machine, and if we don't, we simply return. And then next up, we do much of the same configuration that we've done in our other states. We set the nav agent control so that we have the nav agent controlling our movement but not our rotation. Of course, we set the speed to whatever we configure our speed to in the inspector, and we set seeking to 0, we set feeding to false, and of course we're not attacking, so we set attack type to 0. We also need to set our timer to 0, which remember is going to be used for keeping track of how much time has passed between target repaths, and we also set our target reached boolean to false initially. Finally, we need to set the destination for our nav agent. So we fetch the parent state machine's target position and we set that as the destination for our nav agent. And just in case when we entered this state, some other state had temporarily paused our nav agent, we tell it to resume along its path. Okay then, so let's now create our on update function where all the good stuff happens. So I'll create this underneath my on enter state function. And remember, this is another function that we must override from the base class. It's called onUpdate, and it has to return an AI state type. And of course, by default, we always return the state that we're actually in. So this would be AI state type dot pursuit. And we put that's going to kind of be at the bottom of the function. In other words, if nothing else happens inside this function which causes us to transition into another state, then we return the current state so that our state machine knows that it doesn't need to change state and should just come back and call this on the next frame. So the first thing we need to do is we need to update the timer with the amount of time that's passed since the last update. So we will say timer plus equals delta time. What am I on about? Delta time. It's got to be time.delta time, hasn't it? Yes, like so. And then what we need to also do is, in fact, I just thought of something. Yeah, what we need to also do is we need to check how much time has passed since we began the pursuit state, because we don't want the zombies to just relentlessly pursue the player. We might say something like, if it's given chase for about 40 seconds or something, then it will eventually give up. Now, that's just made me realise that we're going to need two timers then. We're going to need a generic timer, which I'll just leave this one as the generic timer, which is going to be used for keeping track of how long we've been in the pursuit state. But then we're going to need that other timer, our repath timer, which needs to be set back to 0 each time we reset a new path. So, yeah, I'm going to create a new variable for that. In fact, I need to go at the top to do that, don't I? I can't use the same timer for both because one of these timers needs to be reset back to 0 every time we set a new path, and one of them we don't want being reset to 0. We want to keep track of the total amount of time we've been in the pursuit state. So I will call this the repath timer, and this is the one we'll use for keeping track of the repath. And then scrolling down in our onEnterState function, we'll make sure that the repath timer is also set to 0. And then in our update function, we will make sure that we also increment the repath timer by time.delta time. And then what we'll say is, if the timer is greater than a certain threshold, like I said, 40 seconds I used in Dead Earth, then we'll just go back into the patrol state. We'll give up and we'll go back into the patrol state. But to be honest, I should probably make that duration a inspector variable as well. So I'm forgetting all sorts of stuff here, aren't I? So I'm going to create a final variable. Once again, we want this to be a serialized field, so it shows up in the inspector. Once again, it's a private float, and we'll call this max duration. The maximum amount of time we're allowed to stay in the pursuit state. And like I said, I'll set this to about 40 seconds. We don't want the zombie to give up too easily. And then scrolling down in our onUpdate function, we will simply say if timer is larger than our max duration, then simply return AI state type dot patrol. Bum bum bum. Save that off. Let me just go back to the editor a minute, check I'm not getting any errors and that my variables are correctly showing up in my inspector. Well, they're not going to show up yet because I haven't actually added my pursuit state to Zombie Jill. So now I have, yep, and there are all our variables. So the next thing we'll do is we'll check with our parent state machine and we'll see if that in melee range boolean has been set to true, because if it is, then it means that our zombie has managed to get close enough to the player that we should now transition into the attack state. So we'll say if the current target type of our state machine is the player and our in melee range boolean is set to true, well then our course is clear. We simply return AI state type attack, transitioning out of the pursuit state. And of course we're going to see in a future lesson the attack state, and that's going to see our zombie triggering attack animations in the animator. So next up, if we're not in melee range, we really want to check whether we've reached our target yet. You know, whether we've reached the sound source or if it's a food source, for example. So we'll say if that target reached boolean has been set to true, well then we'll do a switch statement and we'll act differently depending on what sort of target it is. If it's food, then we will transition into the feeding state because we've reached the dead body on the floor. But if it's a sound source or a light source, we will go into the alerted state. Once we reach the source of a sound, there's not really a lot we can do other than just transition into the alert state and look as if we're looking for something. Hopefully when we get to the source of a sound, whatever made that sound, be it the player or some other character, will then enter the zombie's view cone and will then trigger the pursuit state again to pursue that target. So we will switch our target type and we will say if it's an audio type or it's a light source type, then all we should do once we've reached the target is clear the target and set ourselves back into the alerted state so that our zombie drops into that alerted state, seeking left and right, trying to find what the source of that light was. Remember, the visual light is the player's torch, so if the player was still there, then the moment the player's collider entered the zombie's view cone, that wouldn't be our visual threat anymore, it would be the visual player. So the only chance that we can get here with the visual light as our original target is if a flashlight was shone from behind the zombie and then the player ran away and then the zombie went to investigate what it thought was the source of that light, at least at the time the threat was first registered. So when it arrives there, the player is no longer there and it drops into the alerted state. If the target type is food, then we're just going to drop into our feeding state, and we'll see later that the feeding state is going to trigger an animation in our animator that is going to see the zombie falling onto all fours and feasting on that dead body. Pretty gross stuff, I tell you. So at this point, we should probably make sure that our path hasn't become invalid or stale or incomplete. And if it has, then there's not really anything we can do. If we're pursuing a target we can't get to, then we should probably just drop back into the alerted state in the hope that we can pick up the target again, pick up the scent for another path, or if after dropping back to the alerted state we don't find another target, the alerted state will eventually transition back to the patrol state and we'll see the zombie giving up and pursuing its patrol route. So we will say if the agent's path is stale, or if for whatever reason it doesn't have a path, or if the path was unable to be completely plotted to the target, then we're going to drop out into the alerted state. Right, so next up we're going to handle keeping the zombie oriented towards the target while it's in pursuit mode. And the first case that we're going to handle is when the target has been reached. So let's just imagine that our player is running around the level, and as our player is running around the level, Zombie Jill is repeatedly setting that player as her new target. And therefore, if we were to see this in the level, we would actually see the player running around and Zombie Jill's target trigger moving around and always sticking to the player. So there's a chance that we could get within the target radius of our target trigger, but not yet close enough to enter the melee trigger of the character. So at this particular point, we're very close to the player and we want to really keep aligned with the player at all times. If we don't, it becomes very easy for the player just to sort of dodge to the left, dodge to the right and get behind the zombie, and then we're outside of Zombie Jill's view cone. She thinks that she's lost her target and she drops back into alerted state, and it becomes delightfully easy to delete zombies. So when the zombie is so close that it's within the target trigger but it's not yet within our melee trigger, then we're just going to every frame adjust the orientation of the zombie so that it's facing the player. So then, assuming we're not using route rotation, and as we know, none of our locomotion animations have any route rotation in them. So if you want to use route rotation in your animations, you would have to slightly modify these states so that they send something into the animator that triggers the turning animation. So you might, for example, have a series of animations in a 2D blend tree where the x-axis is the angular speed and the y-axis is just the straightforward speed. And we did show an example of that much earlier on, but these states are assuming that your animations are not using route rotation, and if they're not, then that means our states have to actually turn the zombie itself. So assuming we're not using route rotation, which we're not, and assuming the target type is the player, and assuming that the visual threat is also the player, and that's pretty important, because just because the target is the player, that target might be the last time the zombie saw the player, but the player may not be there anymore. So if you imagine it saw the player just down the road, and then it went to that position, but then the player dodged behind a building, so the zombie no longer had a line of sight. Well, the zombie wouldn't be able to keep updating its target to the player's new position. It doesn't know what the player's new position is. The player is obscured by a building. So it would just run to the last place it saw the player, and hopefully when it got there, it might see the player's new position, because the player would become a visual threat again, and it would, become the new target that was updated each frame. So what we're saying here is not just if you're at the last location that you saw the player, but if you are at the player's current location, if he is your target and you are currently still registering him as a visual threat, and the target has been reached, in other words, we are now within the target radius of our target trigger, but we're not yet in the melee trigger of our character, well, then we're going to, like I said, rotate Zombie Jill every frame to really keep her sort of glued to the player so she's not too easy to shake off. So we'll first of all get the target position. Remember, this will be the position of our player. And because we want this to be a 2D rotation, we're just really interested in rotating left or right. What we'll do is we'll just overwrite the Y position that we retrieved from the target position with our zombie's own Y position, okay? And then what we'll do is we will create a new quaternion, much like we did in our patrol state, that's going to represent the orientation we wish to be facing. So we do that by getting our target position and subtracting from that our current position. In other words, we're creating a vector from Jill's position to the target position, and that's the direction we want to be facing. So once we have a quaternion that represents that rotation, well, we simply set that straight into the rotation of our zombie state machine. Remember, we're extremely close to the player now. We don't want to be doing a slurp or trying to drag out that rotation, because then it will become too easy when the two are in close quarters for the player to shake off the zombie. So when they're in close quarters like this, we're essentially gluing the rotation of the zombie such that it's always facing the player and always oriented such that if it were to do an attack, it would be correctly aligned with the player's position. Okay then, so we've handled the case where we're in melee range and we're transitioning into the alert state, and we've also handled the case where we're not in melee range yet, but we're close enough to our character such that we're in our target trigger and we want to keep ourselves facing the character at all times. Next up, we'll handle the generic pursuit condition, which is when we're not currently at our target, we're currently running towards it, much like we run between two waypoints. And when this is the case, we want to do something quite similar to above, but we do still want to use that slurp so that we get smooth rotation as the character is running around corners and things like that. So when that's the case, we'll create a new quaternion that is literally just going to face in the direction that the zombie wants to be going. That's our desired velocity of our nav agent. And then once we've got that quaternion, we don't just simply set it as the new rotation of our zombie state machine, much like we did up above, but instead we do the slurp like we do in the patrol state. We rotate our zombie from its current rotation to this new rotation over time multiplied by our slurp speed. So if we get past all of the conditionals that we've just done, and our target reached boolean is set to true, then it must mean that we've reached our target, but our target was not the player, and that means that we've reached the destination that we were pursuing. So what do we then do? Well, simple. If we get to the position of an audio source, once we're there, there's not really anything else we can do if once we got there we didn't see anything visually that triggered us into a pursuit or an attack mode. So we're going to drop down into the alerted mode, which will see our zombie seeking left and right, trying to find, in the case of an audio source, what may have made that sound. And if it was the player that made that sound and he was now heading off in the opposite direction, then when the zombie reached that audio source and started seeking left and right, it might then reacquire the player as a target and then drop into pursuit mode and start chasing him again. So now, just like we've done in other states, we need to check what the current visual and audio threats are, and we need to set them as the current targets if they are of a higher priority than the target that is currently set. So first of all, we'll handle the case where the current visual threat is the player, the highest priority threat. But what we also need to do in this particular case is we also need to make sure that while we're in the pursuit state, we keep recalculating the path to the target if necessary. So I'm going to get the visual threat type, and I'm going to say if the current visual threat is the visual player, then this definitely needs to be our new target. Now, of course, our current target might already be the visual player, so we may not necessarily be overwriting our target, just like with the other states. This is no different to the code that every other state has had, where we just assess the threat types and set a new target if necessary. So we definitely want to set this visual player as the target. There is no higher priority threat, and if it's the target already, then we really need to check whether we need to recalculate the path. But there's no point recalculating the path even if the visual player is the target, because it may not be moving. Just because the player may be moving doesn't mean the player necessarily is moving. So first of all, we'll just make sure that our current target position isn't exactly the same as this visual threat, because if it is, it means this is already our target and it hasn't gone anywhere since the last update, so let's not bother recalculating a path at all. Now we need to see if it's time to recalculate the path, and we do that by taking the distance to the visual threat and multiplying it by our repath distance multiplier, making sure, if I just scroll at the top here to remind you, we clamp the result of the distance with this repath distance multiplier such that it falls within repath visual min duration and repath visual max duration. And if our repath timer is larger than that value, then it means it's time to do another repath. So we'll recalculate the path and reset the repath timer. So let's see what that looks like in code. So we will get the distance to the visual threat and we will multiply it by our repath distance multiplier, making sure that we clamp that returned result between our repath visual min duration and our repath visual max duration. And if we find that our repath timer has now been incremented past that value, it's time to do a repath. So we get the nav agent of our parent state machine and we use its set destination method to set the position of that visual threat as its new target, causing a new path to be calculated. We then reset our repath timer to 0. But of course, whether we need to recalculate a path or not, or whether the visual player was our previous target, we need to make sure that it definitely is our target now. So outside this little conditional where we decide whether we should repath or not, we definitely set this as the new target for our state machine, because there is no higher priority than the visual player, obviously. And then finally, we've done everything we need to do here, so we just return from this state AI state type pursuit, like so. And that is the player totally handled within our pursuit state. Okay, so if we stepped into this code, it meant that the player is currently registering as a visual threat for our zombie. It means the player's collider is within inside our zombie's view cone.
and that position may be ever changing, and therefore that's why we are continually repathing to the target. However, it's quite possible that there isn't currently the player as our visual threat, but we still have a target that is of type visual player. Remember, whichever state we were in before may have picked up the player as a threat and set that as the target, but while we were pursuing that target, the player may have dodged behind a building or just gone out of our view cone such that our zombie no longer has line of sight. Now, when that's the case, we're still going to have a target that is set to the last known position that the player was spotted at. Therefore, if we get down here underneath this conditional, it means that the player is no longer registering as a threat, but the target may still be set to visual player, meaning we do still know the last known location of the player, and we don't want any other threats that may be registering now to undermine that. Remember, the visual player is the highest priority threat, so even if the player is not currently registering as a threat, but we're detecting other threats such as an audio source or a flashlight or some food, if our current target is of type visual player, then we don't want that to be overridden. We want to remain in the pursuit mode, and we want to carry on to the target position, the last known position of the player. And hopefully by the time the zombie gets there, it may reacquire the player's position within its view cone. If our current target type is visual player, then just remain in this state and return. There's nothing else we should do here. We just want to continue tracking to that position. Any audio or visual threats that might be registering themselves with us now are not as important as our original target, the last known position of the player. But of course, we know that when we execute this conditional here, in other words, if our target type is visual player, we only got here because the visual threat was not visual player, which means we know the last known position of the player. But of course, that position is not going to be ever changing. It's just the last place we saw him, so we don't have to worry about repathing frequently to that location. Okay, so if we make it down here past this conditional that we just wrote, then we know a few things. We know that the player is not currently in the view cone and registering itself as a visual threat. And we also know that our current target is also not of type visual player, which means that our current target must be a lower priority threat than that. So what we need to do, like we did in the other states, is we need to assess the rest of the threats that may have registered themselves with our state machine in this update. You know, we may still have threats that are sound sources or the player's light. So after the visual player threat, the next highest priority threat is the player light. So we'll say if the zombie state machine.visual threat type equals visual light, then it means that a light has registered itself with us as a visual threat. But then we need to figure out whether this is a threat that we wish to make our new target. Now, if our current target is a lower priority threat, such as an audio source or a food source, then yes, we definitely want to set this as the new target, and then possibly drop back into the alerted state as well, for two reasons. Firstly, it's going to look really cool dropping back to the alerted state. Imagine, for example, in the game, the zombie has heard a sound. He is now in full pursuit mode, sprinting at that sound source. But when he's halfway there, you shine a light on his back, and that zombie is going to drop into the alerted state, which is going to see him stopping in his tracks and sort of panning left and right, trying to acquire the source of the light as its new target. And if it manages to do that, will then break into pursuit mode and start chasing you. But of course, there's another reason why we wish to drop down into the alerted state, and it's the same reason that we drop into the alerted state when we wish to change to a new waypoint during the patrol state that has a large angle from our current waypoint. And that's because if you imagine our zombie is running in a straight line and then you shine a light on its back, if it was in pursuit mode and we simply set that as the new target, then we would see it on the next frame literally slurp around very, very quickly and start running 180 degrees in the other direction. So by dropping down into the alert state, we also make sure that we don't have our zombie turning through really extreme and unrealistic angles. So what we'll do then is we will say if our visual threat is of type light, but our current target is a lower priority threat, such as an audio threat or, doesn't fit on the screen, a visual food threat, well then what we will do is we will set this as our new target, and then we will return AI state type.alerted, transitioning us next frame into the alerted state that will see our zombie seeking left and right. So the only other thing we have to check in this conditional is whether our target type is currently visual light, the same type that is currently having a threat registered for it. We don't have to worry about whether our current target type is the actual player itself, because if that's the case, we would have already bailed out of the function up here. But we also have to figure out if it is a visual light, is it the same visual light Remember, if we're heading towards the last known location of a visual light threat, that light threat might still be registering itself with us every single frame. So we need to make sure that if we are just heading towards the same threat that we've currently set as our target, then we do similar logic to what we did above. We keep the path updated by continually repathing at regular intervals based on the distance to that threat. Remember, the visual light being the player's flashlight can also be moving, so that's why we need to repath. But perhaps there's another scenario. Perhaps we've got another player in the game and he's also got a flashlight. Now, I'm trying to building in some future proofing here in case we ever wanted to have NPCs with flashlights or perhaps even multiplayer. So it's just something I'm putting in to kind of prove a point. And we're going to need this system in place for dealing with our audio threat in a minute anyway. But the idea being is that just because we're having a flashlight threat registered doesn't necessarily mean it's the same flashlight that we're heading towards. So if it is, we just want to carry on in pursuit mode, heading towards the target, and just making sure we frequently repath. But if it's not the same flashlight, then what we probably want to do is drop down into the alerted state, again setting this as the new target. So you can imagine if the zombie was running towards one flashlight source, then you shone another flashlight on it behind, it would stop in its tracks, panning left and right, and would hopefully eventually acquire the source of the flashlight and start to pursue it. So how can we tell if this visual threat that has been registered is the same light target that we're heading towards? Well, we can use the instance ID of the collider, because remember, if we go back to our state machine and scroll back up to our AI target class, one of the things it stores is the collider. But what we haven't got yet is a means to fetch the instance ID of the collider of the actual target, because the target member of our state machine is pretty protected. We don't just give them access to it. You'll remember that what we do instead is if they want the position or the target type, we had dedicated properties to deal with that. So what we'll need to do is we'll need to create another public property with a getter that's going to allow us to fetch the instance ID of the collider of the currently set target. So I will call this target collider ID, and it's going to have a getter, and it simply says if our target does have a collider. Now, it's always going to have a collider except in the case where it's a waypoint. Waypoint targets don't have colliders, but we're never really going to be in pursuit mode heading towards a waypoint anyway. It's just not wired that way. But this is just a bit of safety. So assuming our target has a collider, then we would just call the collider's get instance ID function. Otherwise, we'll just return -1. So I've added that code there, that property, to our AI state machine base class. Okay, let me save that off. And then if I go back to our pursuit state, we can then do this. We can say else if the current target type is visual light, in other words, our visual threat is a light and our current target is a light, then we will get the current ID of our target by using that new property, zombie state machine dot target collider ID. And now what we need to do is get the collider of our visual threat, which we will have access to, and use its instance ID function to compare it against the current ID. And if they're different, then we know that this is a different light, and we should probably make the zombie drop down into the alerted state. Otherwise, it's the same light, and what we should do is do that whole timed repath calculation. So let's see what that looks like in code. So we will say if current ID equals zombie state machine dot visual threat dot collider dot get instance ID. In other words, if this is exactly the same thing that is registering itself as a visual threat that we are currently heading towards as our target, well, then we're going to do what we did in the case of tracking the actual visual player. We check if the position has changed, then we do that whole repath distance multiplier calculation using the distance to the visual threat multiplied by our repath distance multiplier. And if the timer has exceeded that, then we are going to set that as the new nav agent's destination, causing a path recalculation and setting our repath timer back to 0 before setting this as our new target. I mean, it's our target anyway, but we're just resetting it as the current target. And then we just return AI state type dot pursue. However, if the IDs are different, then we have a new light source that has hit the zombie, and we will make this override the old position that he was heading towards. And this makes sense because once the zombie is actually heading towards the source of a light source, it's going to almost always be an out of date position, because if the player was still there shining the light at the zombie, well then as soon as the zombie is rotated round and has clear line of sight of the player, well then the player is going to be the high priority visual threat, not the player's light anymore. So really this situation is only going to arise if the player was shining a light at the zombie turned around, the player was no longer there, so the zombie starts tracking towards the last place that it thinks that light was coming from, and while he's on his way there from another part of the level, someone else shines a light on the zombie, and that takes precedent. And you can see when that's the case, when the instance IDs are different, we just set this as the new target and we drop back into the alerted mode, which will see our zombie realistically reacting to the new threat, coming to a stop, maybe turning left or right for a little bit to acquire the source of that light. Okay, so now let's handle the last threat that we really care about, and the least priority threat that we care about in this function, which is if an audio source is registering itself with us as a threat. And once again, this will only be executed, see the else, if we haven't currently got a visual threat of any kind. Other than food, which we totally ignore in this. Food will never break us out of pursuit. It can put us into pursuit, but it will never break us out from pursuing something else, because we don't bother processing food in the pursuit state. The food is the lowest priority threat, so if we're pursuing something, food should never be high priority enough that it should make us change our target from whatever we were previously pursuing. So like I said, all we care about is the audio source, and this is going to handle very much like our visual light. In other words, we need to know if it's an audio threat, then if we're currently heading towards food, well no, we need to head towards the audio instead. So we will set the audio threat as the new target, and we will return AI state type.alerted, so that if our zombie was running toward that food source, it would stop in its tracks and it would rotate left and right, trying to ascertain the source of the sound. Okay, so assuming we're not currently heading towards food, in which case, as we've seen, the audio threat would override it as the new target. We now need to check that if our current target is an audio source, is it the same audio source? If it's the same audio source, then because audio sources can also move, we're going to need to do what we did above, periodically repath, so our nav agent has a refreshed path. But it may be a different audio source, in which case, just like with the visual light, that new audio source is going to stop our zombie in its tracks, and it's going to take precedent as the new target. So let's see how that looks. So we're going to say if zombie state machine.target type, if its current target type is audio, and we're having an audio threat currently registered this frame, then let's get the instance ID of the current target, and if it's the same as the threat that's currently registering itself with us, well then we know that we're still heading towards the same audio threat. So we just need to check whether it's time to do a repath. So we just check that the position has changed. If it hasn't changed, no point repathing. And then we do the whole zombie state machine.audio threat.distance multiplied by the repath distance multiplier again. But this time we clamp the value in between the repath audio min duration and repath audio max duration. Idea being here is that we don't really need to repath quite as accurately when we're trying to track the source of a sound, because I don't think a zombie would be able to ascertain quite as accurately where a sound source was coming from as opposed to the position of a visual threat, such as having seen the player. And it's good for us because it means we get away with repathing a little less often in the case of audio threats, which of course will be more performant. So just as we've done in the past with our visual threat, you can see we say if our repath timer has been incremented past that distance multiplied by our distance multiplier, then we will contact our nav agent and tell it to set this audio threat as the new destination, and we will set repath timer to 0 again. We're going to remain pursuing our current target. And of course, we will just make sure that this is still set as the current target for our state machine, and we're done here now. So we will return AI state type.pursuit. We're just carrying on towards our current target. But if the audio threat that has just been registered with us has a different instance ID from the audio threat that's currently set as our target, well then we'll make this one take precedent, and we'll simply set it as the new target, and then we will return AI state type alerted. So I think that's pretty much our pursuit state done. Let me save that off. So when we go back to the editor in a moment and we run our code and we put our pursuit state through some tests, we're going to see some problems, some little glitches, little things that are not working the way that they should. And in fact, this is going to be due to a few minor design flaws in our AI system. Now, at the start of this series, way back in lesson 1, I did say that I was going to try and do an authentic coverage of the development process, warts and all access if you like, including me making the mistakes as I go along. And in fact, I am developing and designing these systems as I record the videos. So there's always a chance that further down the line I might have overlooked something and have to go back and fix it or change the design slightly. And having done a dry run of this lesson before I pressed record, I can tell you we have such a situation now. So let's go back to the editor, press play, and basically see how this all pans out. So in this scene at the moment, I've set up two game objects to be two mock audio sources, much like we did at the end of the last lesson. If you look in the scene hierarchy, you can see I have two disabled game objects. Let me enable them both for now, so you can see where I've placed these mock audio threads. We have one down here, the same position we had it at the end of the last lesson. I've placed another one in this room over here. You're reminded that in order to mock an audio threat, both of these game objects have been assigned to the audio aggravator layer and have been tagged with the AI sound emitter tag. So let me turn them both off, and what we'll do is we'll press play and we'll wait for Jill to get sort of around the other side of the bus, heading towards her first waypoint, and then we'll temporarily just turn that first sphere on to emulate a sound source that is on for a second or two, and we'll see Jill break out of her patrol state, go into an alerted state, acquire the target, and then sprint towards that source. So let's see that happening now, and we'll do this in the scene view so we can see it more clearly. So she's on patrol. I'll wait until she's facing away from the sound source, then I'll turn it on temporarily. She's heard the sound. She's now trying to figure out where it is, and now she sprints to that location. And as you can see, once she gets there, she stops there wondering what's going on. If I then enable the other sound source over there, you can see she's heard that sound source, and she goes to investigate there as well. Once again, if I enable the other sound source, you can see her starting to run back, but you can also see the sound interruption as she heads towards this one. If I enable the other one, the more recent sound source interrupts her path, and she's going to go and see that one again. You can see me do it again here, where I enable this foreground sound source, and you can see her stop, and she's in the alert state. You can also see one of the problems here, where she's kind of stuck, going forward and backwards for a little bit. And we'll solve that problem as well. But the biggest problem that I want to focus on at the moment is what happens when she actually gets to the source of a sound, if the sound is still emitting. And this is something that I didn't really find very easily in my demo, because my sound sources were all things that just emitted for a second or two and then stopped. But you can see if it was something like a car alarm that was continually emitting, you're going to see this really strange behavior where she just runs round and round and round and round like so. Pretty nasty stuff. There's a few other glitches here as well, but we'll focus on this one first. So if we take a look at our pursuit state once again, you will remember that we have this private boolean called target reached, which we use to keep track of whether the zombie has arrived in its target trigger or not. And it's set to false when we first enter the state, but you're also reminded that our parent state machine has the on-trigger enter and on-trigger exit functions to trap the message that Unity sends it when our zombie's body enters its target trigger. And those two functions call the child state's on destination reached function to let us know it's either arrived or it's leaving its target. The problem here is that this is a little bit of a design flaw, because it works fine for something like our patrol state where we are both arriving and leaving targets all within the same state. But the problem with our pursuit state is that it will often drop back into the alerted state, and then the alerted state back into the pursuit state. If we scroll down a little bit in our pursuit state's on update function, you can see quite near the top we say if the target has been reached and it's an audio source, we'll then just clear the target and drop down into the alerted state. Remember, if a zombie actually gets to the source of a sound, it can't really do anything, not if it hasn't been able to acquire a visual target whilst on the way to investigating that sound source. So what we do by design is once the zombie enters the target trigger, if the target was an audio source, then we just want it to really just drop back to the alerted state and just stay there looking alert and looking concerned until the alerted state's max duration is reached, and then it will give up and go back to its patrol state. Okay, so herein lies the problem. So our zombie hears a sound, Okay, it's in the alerted state, it hears a sound, it gets put into the pursuit state with an audio type target. It runs towards the target, and when it gets to the target, the parent state machine will call our onDestinationReached function, setting target reached to true. Okay, so now all is good. And while we're in this state, until we've reached the target, this code will be getting executed, just slowly rotating our character to face the target until it reaches the target. And when it reaches the target, it will drop down, like you said, from this switch statement into the alerted state. Okay, now let's take a look at the alerted state. When we're in the alerted state, this has no concept of whether a target has been reached or not, and certainly no concept of that Boolean variable that was set inside the other state, the pursuit state. So in this code, if we just scroll down a bit into the onUpdate function, we can see that it will most likely acquire the same audio target again, the one that we've just reached in the pursuit state and then drop down into the alerted state. When it acquires it again, it will measure its angle, and assuming that the threshold is small enough, which it will be, it will put us back into the pursuit state again. So we've almost got a situation here where we're ping-ponging between pursuit and alerted, but the situation is even worse than that, because the next time we go into the pursuit state, in the onEnterState function, we set target reached back to false again, but we never get a notification telling us that we are still at the target, because remember, the parent state machine is only trapping the onTriggerEnter and onTriggerExit functions, and whilst we jump down into the alerted state and then back into the pursuit state again, our zombie never left the target trigger, therefore no other notifications, certainly another onTriggerEnter message, was going to be generated. So we now find ourselves inside the target trigger in the pursuit state, but not knowing that the target has been reached, and no way for it to know the target has been reached. So what happens is this code is ignored, so we don't keep dropping down into the alerted state again, at least, and ping-ponging backwards and forwards between the two states. But what does happen is, because the target reached is never set to true, because we never left and re-entered our target trigger, this code is continually executed. So our zombie is stuck just trying to slurp its rotation around to look at the target. So that's why we're just seeing it run round and round in circles. So let's go back and remind ourselves what this looks like. But this time, once I've enabled the sound source, I will then click on Jill's target trigger so we can really see what's going on. So I'll wait for her to run around the other side of the bus, then I'll activate the sound source and I'll select her target trigger. So she's alert, she finds it, she goes into pursuit mode, and do you see what happened? When she got into a target trigger, she dropped down into alert mode, and then while she was in alert mode, she rotated around again, reacquired the position of the target that had managed to get behind her, and then she goes into the pursuit mode again. But because she never left the target trigger, our pursuit state is never notified that we've entered or have remained inside the target trigger, so she stays in this loop forever, trying to reach the target, which never gets flagged as having been reached. So the way we need to address this problem is there's a couple of things that are wrong. First of all, we need a more global variable that any state can use to detect whether we are at our target trigger. And the best way to do that is to store it and process it in the parent state machine. So what we're going to do is go back to our AI state machine base class, and we will add a new protected variable of type Boolean, and it's going to be called isTargetReached. The idea being is that if we can store this in the parent, then any child state can ask the parent state machine whether we're at the target, and we no longer have this problem of a Boolean that is set in one state just isn't accessible via another state. So we will set this to false by default. And we'll also want to create a public property so that our scripts can access that Boolean. So I'll create a public Boolean property called isTargetReached. Only needs to have a getter that simply returns our protected variable, like so. Okay, so the next thing we need to do is we need to make sure that this isTargetReached Boolean is set to true and false when we enter and exit the target trigger. So let's go down to our parent state machine's onTriggerEnter and onTriggerExit functions. Here they are here. Remember, we implemented both of these functions to trap when the zombie's body collider enters the zombie's trigger collider. Remember, this isn't the same as the onTriggerEvent function, which is one of our own functions. This isn't a function that's called by Unity. All of our usual threats, such as our sounds, our lights, and even the player's body collider, they are all registered with the sensor trigger. and we have this sensor trigger script, which then passes that onto the parent state machine's on trigger event function. Now, we've covered all this already, but I'm just reminding you, because when we're looking at the parent state machine on trigger event function, it's easy to forget, so many lessons ago, how it's being used. So all of our threats come in via this function, via our sensor script. So the on trigger enter and the on trigger exit functions is only going to be sensitive to triggers or colliders that are collidable with the zombie's actual body, which is on the AI entity layer. And that's things on the AI entity trigger layer, such as our target trigger and our melee trigger. But we're only interested in the target trigger. So you can see in our on trigger enter function, if it's not the target trigger, we bail. Otherwise, we notify the child state that we've arrived at our trigger. So let's now set our new is target reached boolean to true here, and go down into the exit function and obviously set it to false there. But this actually doesn't cover all cases. There can be special cases in Unity where if a game object is destroyed with a trigger on it, the actual object doesn't get the on trigger exit notification. So to be absolutely safe, what we should do is we should also implement Unity's on trigger stay function. This is a function that is going to be called by Unity each physics update that our zombie remains within the target trigger, and we'll make sure it's being set to true there as well. And here is what that function looks like. It looks just like the on trigger enter function, except that we don't bother notifying the child state for stay cases. Actually, I've just noticed that on trigger exit should probably be protected, not public. So let me fix that while I'm here as well. Okay, so we now know that our is target reach boolean in our parent state machine is always going to be set true when we're inside target trigger. But like I said, there are cases when we might fail to get an on trigger exit function. So I think just to be safe, because we know we're going to be setting this boolean to true whenever we're inside it, each physics update, we can go back to our fixed update function, and with each fixed update we can make sure that we set that value back to false. We're saying is target reached equals false. So using this method, at the beginning of each physics step we are setting it to false in fixed update, but then after that, when the trigger messages get fired, we're going to be setting it to true if we find that we are inside the target trigger. So now every state can get accurately whether the parent state machine is in the target trigger or not. So now that we've got that, we can now go back to our pursuit state and get rid of that target reached boolean. In fact, we can even get rid now of the on destination reached function. We just don't need it because we're just going to use the parent state machine's is target reached property instead. So we'll get rid of that boolean as well, called target reached. We no longer need it. That information is stored in the parent state machine. We'll also remove it from the on enter state function, because that variable no longer exists. And wherever we referenced our target reached boolean in this code, we're now going to change it to zombie state machine.is target reached. So we have one case there where we're testing to see if we're at our target, and if so, whether we drop into the alerted state or the feeding state. We also have one, I believe, at the end of this line. Yes, there it is over there. This is the clause where we're checking if we are currently in the target trigger and our current target is the player. We just make sure that if we've reached the target but we're not in melee range yet, then this code will be executed. So once again, let's update that. Zombie state machine is target reached. Another one here. And I think this is the last one down here. So let me also... That's cool. So we've replaced all of the local boolean target reached with the parent state machine is target reached property call. So that solves most of the problem, but not quite, because if we go back to our alerted state, we are reminded that when we find that we are tracking an audio target or a visual light, and we find that the angle is pretty shallow, in other words, we're facing in the general direction of that threat, well, then we go into pursuit mode. And this is part of the problem that we were seeing before, because we were in pursuit mode, we then arrived at the target, and then we dropped back down into the alerted mode. But then when we're in alerted mode, our target is still that audio target, or if it isn't, it will be acquired again if it's in front of the zombie, and we'll get put into pursuit mode again to go after that same target, and we'll spend the rest of our days endlessly ping-ponging between our alerted state and our pursuit state on alternate frames. So what we really need to do is we need to say, if the target is an audio or it's a visual light, only go into pursuit mode if we're not already at the target. If we're already at the target, there's nothing to do. Don't do anything. Just stay in the alerted state, looking concerned about the sound that you've heard. So that's pretty easy to fix. Just on this code here, we'll put the or in brackets. So we're going to say, if it's an audio threat or it's a visual light threat and we're not at our target. So we'll say if not zombie state machine dot is target reached, then we won't go into pursuit mode again. Okay, we don't go into pursuit mode if we're already there. Makes perfect sense now. I can't believe I missed this in my first implementation and my first design of this system. So that should solve that problem. So let's check it out and see if it does. Oh, I've got errors. What have I done? Oh, I forgot. Sorry guys, I forgot to change the name of that function. That's copy and paste for you. It's supposed to be on trigger stay. That's because I copied it from on trigger enter down to there and forgot to rename it. So that should now work. We now have enter, stay and exit flavors of the on trigger functions implemented in our parent state machine. Okay, so if I press play now, I'm really hoping this is going to solve that particular problem. Okay, so Jill is on a patrol route. The sound is emitting and I leave it emitting because that's when the problem rose its head. It arrives at the sound source, it drops down into the alerted mode, but when it's in alerted mode, even though it knows it still has this audio target, it checks with the parent state machine and says, hey, I'm already at the target, I don't need to go into pursuit mode again, and all is good. If I turn off that one, he's enable the other sound source. She's now going to go running over there, and let's just check it works over here too. And there you can see she stays there saying, what is that sound? What is that sound? Why can't I see anything? And of course, if it was you that made the sound, firing a gun or having noisy footsteps on a tin floor, then by the time she gets there to investigate the sound, you might enter a visual range, and then you would become her new target. So that's the first problem fixed, and a slight tweak to the design of our state machine. But there's still some more problems that we'll look at now and that need to be addressed. Okay then, so to demonstrate the next problem, I'm going to run our application again, and this time I'm going to wait until Zombie Jill has run past our sound source, then I'm going to turn the sound emitter on and then turn it off again. We're going to see Jill stop, track and pursuit to the location of the sound source, and then the problem that you're going to see is what happens when she gets there. She's going to drop into the alerted mode exactly as we want her to do, and she will stay there until the alerted state's max duration has expired, and then she will go back into a patrol state. So let's see what happens when we get her to do that. It seems a rather subtle problem, but it's actually one that's going to require a bit of refactoring in order to fix. So here we go. I'm going to enable the sound source, then I'm going to turn it off again. She's going to find where the source is coming from. She gets there and she drops into the alerted state. Now she's going to stay there until the max duration that she can stay in the alerted state has expired. But look what happens. In order to get back onto a patrol route, she has to run forward a bit first, then drop into alert mode again before she can reacquire her waypoint path. So what's basically happening here is that our patrol state, and if I call up Zombie Jill, make it a little bit easier to see, our patrol state is the state, and the only state we have, that knows about the waypoint network. We're currently assigning it to the patrol state itself. So when Zombie Jill arrives at the target, she drops down into the alerted state. Once the time has expired that she's allowed to stay in the alerted state, what she really wants to do is, if she's facing away from the next waypoint, she wants to rotate on the spot while in the alerted state and head towards that waypoint. The problem is, in the alerted state, she has no idea what her next waypoint is. Therefore, what we do currently, if I call up the alerted state and scroll down to the onUpdate function, you can see that if the timer has reached 0, then time is up, we've been in the alerted state too long, and we simply return to the patrol state. Now when we go into the patrol state, Zombie Jill is going to set her speed to the patrol speed before she realizes that her next waypoint has been set and she has to drop down into the alerted mode again. When she drops down into the alerted mode again, of course everything is fine then, she knows her target is set, so she seeks left and right until she gets her steering path within her visual view cone or within her turn on spot angle. The problem is, by making her drop from the initial alerted state into the patrol state just in order to set her next waypoint before dropping back into the alerted state again, means that while she's in that patrol state for a fraction of a second, obviously the speed value is going to be sent to the animator, that's the patrol speed, and we're going to see the locomotion animation play, making her run forward a few steps. What we really want to happen is we want to say, if she is in the alerted state and she has been here too long, then rather than just blindly go back to the patrol state, what we should do is we should try and get the waypoint ourselves and set that as our new target right there within the alerted state. And if the angle between the direction that she's facing and the direction that she wants to go is a big angle, well then she's going to stay in the alerted state, seeking left and right. And of course we know in the alerted state that if the angle was directly in front of her, well then she would go straight into the pursuit state. So in order to do that, it's a simple fix. We just really need a way to say in the alerted state, our time is up, we want to reset the new target without leaving the alerted state. But in the alerted state, of course, we don't have access to the waypoint network. So what we need to do is we need to rethink our design a little bit. We no longer want our patrol state to be the thing that owns the waypoint network reference, but instead I think we want to move that into our parent state machine as well. So I'm going to call up my patrol state and I'm going to copy these first three variables, where in our patrol state we have the waypoint network, whether it's going to be a random patrol of that network, and also an integer that's used to keep track of the current waypoint. And I'm going to delete them. I'm then going to go back to our AI state machine class up here, and I'm going to add these in our serialized field block. That's where all our serialized properties are, and I think I should probably make these all protected as well so that any derived classes can access them. Okey-dokey. So what we're going to do now is, for any state that wants to be able to get the next waypoint or just inquire about the current position of the currently set waypoint, we're going to implement some functions in our base AI state machine class that's going to do that. So before we do that though, let me go back to our patrol state, because we've just ripped those variables out of there, and as such we're going to have sort of errors now in our code where we're trying to access a load of properties that we no longer need to access because they're no longer accessible. So what we'll do is, in our onEnterState function, this bit where we're setting the first waypoint when we first enter the state and setting the new target, etc., we are going to totally get rid of all that stuff completely. It's going to greatly simplify the onEnterState function of our patrol state. So what we'll do as a replacement for all of that code that we just deleted, which you will recall is the code that basically makes sure that we have a valid waypoint when we enter the patrol state, is we will simply rely on the parent state machine to do that. And we'll implement a function in the parent state machine called getWaypointPosition that will just return the position of the currently set waypoint. So then all we have to do in our onEnterState function is just say zombie state machine nav agent set destination, and of course as the destination it takes a vector 3, so we will use our zombie state machine's get waypoint position function for that. Remember, we haven't implemented this function yet, we're going to do that afterwards, but let's pretend that we already have that function implemented, and that's just going to say this is the position in 3D space of your next patrol point. Zombie state machine dot get waypoint position. Obviously this is going to give us an error at the moment because we haven't implemented that function. And I think what we'll do as well is we will make this get waypoint position function take a Boolean property that can either be true or false, and that will instruct the function how, when we wish to retrieve the position, do we wish it to actually increment onto the next waypoint in the path before it returns that position. So if we pass in false, it will just return the position of the currently set waypoint, but if we pass in true, it will increment the current waypoint, fetch the next waypoint in the list, and return that position to us. So we've got a single function here that is dual purpose. It not only gets the position of the currently set waypoint, but it also gets the next waypoint in the list. But of course, in our onEnterState function, we will simply pass in false. We don't wish to increment the waypoint counter because we might not have arrived at our target or anything like that. We just want to say whatever the waypoint was currently set to when we entered into the patrol state, then then that's the current waypoint we wish to be heading towards. So scrolling down our function, we also now have this next waypoint function, which I'm going to comment this out for now. In fact, I'm going to copy our next waypoint function, which remember is what's called by this state when it realizes that it's reached its current waypoint and wants to roll on to the next waypoint. I'm actually going to cut that from our patrol state completely. I'm going to copy it over into our AI state machine class. Now don't get me wrong, this is not quite ready to go yet. We're going to get errors when we paste it in here, but don't worry, we'll come back and address this at the moment. The main thing is that we've moved it out of the patrol state, okay? So of course in the patrol state now, we have a few places where we actually call the next waypoint function that's no longer a method of our patrol state. So what we'll do instead is we will replace that call with a call to our zombie state machine dot get waypoint position function, which we also haven't written yet, but this time we're going to pass in true, okay, because the next waypoint function is called when we've either reached our destination or if for whatever reason the path to our current waypoint has become stale or is incomplete, in which case we just used to call next waypoint. So if we call get waypoint position and pass in true, then that's the same as doing next waypoint. It will just instruct the parent state machine to increment its current waypoint counter and move on to the next waypoint in the list. So we also need to copy that down into our on destination reached function, so that now all waypoint processing is going to be done in the parent class. Okay, so our patrol state has now been relieved of any management of the waypoint network and keeping track of what is the currently set waypoint target. And we've moved all that into our AI state machine base class. So let's now go back to our AI state machine base class where we just pasted in the next waypoint function, and let's try and get this working. So I'm going to create another function above that, and that's going to be the function that is the public function that everything calls to get the waypoint position, and it returns a vector 3. And what did we say it was going to be called? Get waypoint position. And we also said that this can take a boolean that will allow us to determine whether we should increment the waypoint before we return it. So I'll call this increment, like so. Now one of the things that we need to do in the get waypoint function is we need to know the very first time it's called, because the very first time it's called we wish to set the waypoint to either the first waypoint in the list, or if it's a random waypoint, choose a waypoint randomly. So let's go back up to our variable declarations in our AI state machine class, and let's make sure that when the state machine is first created, that the current waypoint is set to -1. Now that will only ever be set to -1 the very first time that a call to our get waypoint position function is made. So what we'll do is the following. We know that if current waypoint is -1, then it's the very first time this function's ever been called, so we definitely need to set current waypoint to a valid waypoint index. Now if we currently have set this state machine to do a random patrol of the waypoint list, well then we just set the current waypoint index to a random number between 0 and the number of waypoints in our list. But if it's not a random patrol, then we definitely want our current waypoint to be set to 0, the first waypoint in the list. However, if current waypoint isn't -1, then this isn't the first time this function's been called. So we need to increment the waypoint counter if that increment boolean has been set to true. So you can see I say else. If we've been told to increment the waypoint, then we're going to call the next waypoint function down below that's going to take care of actually incrementing the waypoint. So what we want to do now is we want to go down to our next waypoint function, and we want to sort of refactor some of this, because this bottom bit where we used to actually, once we had the current waypoint index, fetch the waypoint from the waypoint list and set it as the target, we kind of really want that not to be in this function anymore, but to be in the function above it, the get waypoint position function. All we want the next waypoint function to do is just deal with incrementing legally that current waypoint index. And you can see we covered this when it was part of the patrol state. We simply just say that if it's a random patrol and we have waypoints in our list, and then the next thing we do is we just make sure that we definitely generate a random waypoint which isn't the current waypoint. Because obviously when we generate a random number between 0 and the number of waypoints in our waypoint network, it might return back the same number that we're currently heading towards. So we do that by just recording what the current waypoint was, and then we enter a while loop that basically says continue doing this loop while current waypoint equals old waypoint, and then we set current waypoint to a random number. Otherwise it's not a random patrol, and you can see that we literally just increment the current waypoint but if that takes it past the number of waypoints in our list, then we wrap it back round to 0. So now up above in our get waypoint position function again, we're going to paste in that code that used to be down below, which was the one that once it had the actual waypoint index would take care of fetching that waypoint from the waypoint network and returning its position and setting it as the new target. So we're going to need to change some things here because it's referring to the zombie state machine, but of course that was when it was in the patrol state. We no longer need to actually access the state machine because we're in the state machine itself, so we can call the set target function directly like so. And likewise, we don't need to do zombie state machine.navAgent. We can just access our navAgent variable directly and call it set destination function. And once again, as we set the target and we set the distance to the target, we can just do transform.position, not state machine.transform.position. So if we look at our get waypoint position function now and just briefly step over it, you can see that if the current waypoint is -1, it's the first time it's been called. So if it's a random patrol, we generate a random waypoint index, but if it's not a random patrol, we set it to 0, the first waypoint in the waypoint network. Otherwise, if increment has been passed as true, then we call that next waypoint function to essentially increment our waypoint index, handling the case where it's a random selection, or if not a random selection, handling wraparound back to 0 when we exceed the number of waypoints in our waypoint network. So when we get down here, we now have our current or new waypoint index. So what we need to do is we need to fetch it from our waypoint network, and assuming that it's valid, it's not null, then what we're going to get back is a transform. So you can see we say new waypoint equals waypoint network.waypoints, and of course we pass in our current waypoint as the array indexer. And now we have the transform. We can set this as our new target. So we set target, type waypoint. We don't have a collider for waypoints, so we're just passing null, and we set in the new waypoint's position and calculate the distance. Now the only thing we want to remove from here is the bit where we automatically set this as the new destination for the navAgent. You'll notice that when we go back to the patrol state where we ripped out all of that stuff at the beginning that used to do the whole waypoint selection stuff, we do still expect to set the navAgent's destination ourselves. So you can see in the patrol state I say navAgent.setDestination, and then I call that get waypoint position function. And the reason I don't like making the navAgent destination setting a responsibility of the state machine's get waypoint position function is because there may be times when we wish to increment the waypoint without actually telling our navAgent to assume a new path. So I'm going to take that out of there. So we set it as the new target, so our state machine knows that this is where it's supposed to be heading, but we're going to leave it as the responsibility of the current state to actually set that destination of the navAgent. So if I save that off now, I'm probably going to have a whole catalogue of errors when I go back to the editor, because let's face it, we've chopped some stuff about here. Okay, I have something. Oh, what a fool. Of course, the whole idea of the get waypoint position function is it's supposed to return a position. So of course, once we've set the target, we need to actually return that. So we'll say return new waypoint dot position. Of course, we'll still get an error because if for whatever reason the waypoint in the waypoint network was null, then we're not going to step into this clause, and there's not going to be any line that actually returns something from the function. So I think what we'll do is, in the default case, we'll just return vector3.0. About all we can do, really, I think. And I'm also going to put some comments above that get waypoint position function, like so. And if I save that off, go back to the editor, hopefully the errors are gone now. Yes, they are. So we now have our patrol state relying on the parent state machine for its waypoint management. But of course, the problem that we were seeing was actually in the alerted state. If you remember, what we were saying was when we were in the alerted state, in fact, let me call up the script, and when our timer has reached 0, which means we've been in the alerted state too long, well, then we drop back to the patrol state. So even with those fixes that we've just made to the patrol state, that hasn't solved the problem. That was just the first step. That was getting the waypoint network and the management of that network out of the patrol state into a more global place so that any states, and in our case, our alerted state, can query the currently set waypoint and set a destination to it without leaving the alerted state and forcing it back into the patrol state. So let's do that now and fix that problem. So we're going to say that if we've been in the alert state so long, it means that we're going to give up now on the current target that we're tracking. So imagine it was an audio source and we've arrived at the source of the audio. We've seen nothing there. The time has run down on our timer, and now it's time to select our waypoint and start heading towards that. So instead of going back to the patrol state, what we'll do is this instead. We will, from our alerted state, call the zombie state machines, get waypoint position function, passing in false. What we're basically saying here is that if we were on our waypoint network and we heard a sound and then we deviated off of our patrol route to investigate that sound, now that we've given up trying to track the source of that sound, we want to resume towards the waypoint that we were currently heading towards prior to dropping into this state. So we don't want to pass through because that would go on to the next waypoint in the list. We just want to go back to the one that we were currently visiting before we got disturbed. So that's going to get our 3D position, and then we're going to pass that in as the destination of our nav agent. So remember, the get waypoint position function also sets the waypoint as the current target of the state machine. So when this line has been executed, not only do we have the waypoint set as our state machine's target, but we also have it set as the destination of our navigation agent. So then finally, we tell our nav agent to resume, just in case for whatever reason the nav agent was in a paused state. We tell it to resume so it starts to navigate along its path. And then we set the timer back to max duration again so that we don't leave the alerted state. And that's really important because what we've done here is we've kind of simulated going into the alerted state again fresh, but without having to leave it and go into another state. Because although we're staying in the alerted state, our target has now changed. Before it was perhaps the source of a sound threat, but now we've set it back to a waypoint. So it should have that same amount of time to, rotate on the spot to get the waypoint within its field of view so it can start to patrol again. So the great thing about this system now is that we no longer have to have a special case piece of code that forces it into the patrol state. It's actually going to happen naturally now, just based on what we already have in the function, because all we've done is set the new target. And of course, if we go down to the bottom of the onUpdate function, you can see that if the current target is a waypoint and that waypoint is within its waypoint angle threshold, then it's going to step into the patrol state. Otherwise, it's just going to continue seeking left and right until it gets the waypoint target within its waypoint angle threshold. Okay, so looks like it should be pretty good. Looks like our problems should be fixed, but you're going to see that they're actually not. There's one more small little tweak that we have to make to fix this problem. So let me run it again and do the exact same test again with our little mock sound emitter. Oops, I'm getting a object reference, and I know why that is. What an idiot. Okay, so of course we removed the AI waypoint network reference from our patrol state into our state machine, but we forgot to assign our waypoint network to our state machine now. So if we call up OmniZombieGeos AI entity game object, and we now look in our state machine, you can now see we have this new slot where we can assign our AI waypoint network. Remember, this used to be on our patrol state, but it no longer is. So we will drag over waypoint network 1 and assign that to our zombie state machine. To be honest, it just feels nicer. The state machine itself, maintaining a reference to the waypoint network, just seems more intuitive somehow. And you can see that current waypoint is set to -1, and I don't currently have this set as a random patrol. So now if I run this, we should see our zombie behave as she did before. Thank goodness. Okay, so let's wait until she's run past the threat. I'm now going to turn the sound on, then I'm going to turn it off. We're going to see her pursue to the position of that threat, and then when the time has expired, we would like to see her just rotate on the spot and not do that leap forward, because we've done all that code to fix the problem. But look, she still lunges forward and in fact gets herself in an even bigger pickle this time. So what's happening here? Well, what we're seeing here is a bit of a race condition. If we go back to the alerted state, what we're essentially doing is setting a new target and a new path for our nav agent in the onUpdate function. And then when we get down to the onUpdate function, within that same update, and if the target is a waypoint, then we start measuring the angle, etc, etc. The problem is that the nav agent set destination functions are actually asynchronous, so there's a good chance by the time we get to the bottom of this function, the path hasn't been computed yet. It's happening in a different thread. So what we need to do is also make sure that we only step into this conditional and even try to seek to the target if the path is not in the process of being computed. So we would do that by amending this final clause and by saying if the target type is AI target type waypoint, and if our zombie state machine's nav agent is not currently in a state called path pending, which means the path is currently being computed, we won't try and use that target yet. We'll just assume that we kind of haven't got a target, and then on the next update, probably the next frame, when the path is computed, we will step into this code and we will start trying to seek towards that target. So let's see if that solves our problem. These are the little things you have to think about. The fact that pathfinding is not a synchronous operation in Unity, and therefore you may have little race conditions like this. And I may not have caught them all either. We may find as we develop this code, we find a few other little instances where we may have to, check that path pending boolean or status, sorry, and make a change depending on what it says. Okay, so let's see if she still lunges forward. No, she doesn't. See that? Now she stays in the alerted state. We set her target, and because she's in the alerted state already, she simply starts spinning on the spot, trying to acquire the original waypoint that she was heading towards. Very, very cool stuff. So that's our second problem fixed. So the last problem we need to fix is more of an oversight really when I was implementing the alerted state. And to best show this off, what I'm going to do is I'm going to select Zombie Jill's AI entity game object, and in her zombie state machine I'm going to turn her intelligence all the way down to 0. Now you will remember that when we are in our alerted state, just zoom in on the code a bit there, you can see that if the random value that we generate between 0 and 1 is smaller than our intelligence, then we always seek intelligently based on what the sign of the angle is between our forward vector and the target. However, if we're not very intelligent, let's say for example we have an intelligence of 0, then this conditional will never be executed. This one always will. And you can see in this particular case we choose a random direction by essentially choosing a random number between -1 and +1 and then taking the sign of that value. So in other words, we're assigning it either -1 or +1 randomly. The problem is this code is executed every single update. So when we have a non-intelligent zombie, this code is being executed, let's say 60 times a second, and obviously the direction's being changed from one frame to the next. So we're just saying left, right, left, right, left, right, right, left, right, left, left, left. So that's what you're seeing in the view here. If I press play and we wait until Zombie Jill gets around the other side of the bus, and then I'll enable the mock sound, and you'll see what happens. Remember when I turn this sound on, what's happening now is she is just randomly choosing a new direction to turn each frame. And as you can see, that's constantly putting our animator between left, right, left, right, left, right, like so. Now, when I said it was a oversight when I was developing the alerted state, that's kind of not really true. I basically thought I was going to do something one way, and it turns out I'm going to do it another way now, which means I need to add a little bit of code to my alerted state to address this issue. You see, what I thought I was going to do was use the fact that in our animator we can click on any of the transitions, such as the transition from left to right or the transition from right to left, and we can tell it that it has an exit time. And in this particular case, the exit time is set to 0.9. Now, with these booleans ticked, what it basically means is even if we were switching the random direction from -1 to +1 very, very quickly, it would only actually do something to the animator once the animation had played out in its entirety. And then it would check the seeking value again and then decide to go left or right or whatever. And that would actually solve that problem. So what we'd be basically saying is when we decide to turn left, we want the animator then to never interrupt its state until it gets to the exit time. So a full pivot to the left would be carried out before it really used that seeking variable again to choose whether it needs to seek to the right or carry on seeking to the left. However, the reason I decided against this is because we don't want to be stuck in a situation where we are always having to have our zombie turn animations play out in their entirety to their exit time, because we can see a potential downside of that. So let's imagine that our view cone is pretty cool and this object is just to the left of us. We set the seek direction to -1, the zombie turn left animation plays out in its entirety, but in that time we've rotated so far around to the left that our threat has actually exited now the opposing side of our view cone. So we always want to be able to come out of our zombie turn left and zombie turn right states immediately when we want to, when we see a threat that is in our view cone. So what we're going to do instead is we're not going to force the has exit time boolean on, but we're going to add a timer in our alerted script so that we never change direction more than say once every 1.5 seconds. But
we will still be able to, if we see that a threat is within our view cone, just like we do now, transition straight to the pursuit state, which will cause us to exit out into the idle state and then into one of our walk, jog or sprint states. So in order to do that, I'm going to call up my alerted state, and I suppose we should really add a new timer for this. So I'm going to call this timer direction change timer, and of course I will set that to 0 by default. And I suppose I should also add a serialized field that we can set via the inspector that is going to allow us to configure how long the actual wait state is going to be before our zombie can choose to change direction and start seeking in the opposite direction. So we'll make this a float as well, as it's going to be a time specified in seconds or fractions of a second. And I will call this direction change time. And let me just make sure, because it's a private variable, that I switch that for a small d after the underscore. So now we're going to go down into our on enter state function, and we're going to make sure that we also set that direction change timer to 0, like so. And then in our on update function, we're just going to make sure that we add time onto that timer. And of course, you know the drill by now, we add on time.delta time. Okay, so now we'll scroll down to near the bottom of the on update function, where we decide that we have a target and we wish to check the angle. And if I just remove that debug log a moment that I was just using before I pressed record for doing a bit of debug output to find out what was causing this problem, you can see we don't have to do anything here. This is where we just say if the audio threat is within our view cone, then we're going to go into pursuit mode. But if that's not the case, then it means we need to either seek left or right, either randomly or based on our intelligence settings. So what we need to do then really is just make sure that we wrap this in a conditional that just makes sure that the time is right for us to be able to change direction. So we will say if direction change timer is larger than direction change time, then we will step into this code and we will allow the zombie to make a direction change. But of course, underneath that, just before we leave this conditional, we need to reset the timer again. So we'll say direction change timer equals 0, so that we won't be able to make another change in direction until our direction timer has been incremented past our direction change time. So I think now if I go back to the editor and just check I haven't got any errors, and I haven't, and I'm going to leave Jill's intelligence setting at 0 because this is the easiest way to check this problem. So let me get ready to enable that mock audio sound. Come on, Jill. There you go, she's off. So I'm going to wait until she's facing away from the audio threat, and then I'm going to enable it. And you can see now she's changing randomly every 1.5 seconds. And look, she did eventually get lined up with the target. So I think that problem's solved. There's also another case where this can happen, which I think this will probably solve. But I just need to make sure that it definitely does. And if it doesn't, then we'll come back later and fix it. But the other case it can happen is when the sound or the target that we're tracking is exactly or close to 180 degrees behind Zombie Jill. Because if I just put Zombie Jill in the alerted state for a second by enabling that sphere and then selecting her transform, you can see that when she goes into the alerted mode, you can see that her transform is being animated by the animation. So you can imagine now, if I was a threat behind her and we were doing that angle calculation, it could actually fluctuate. So for example, 1 minute it might be 179 degrees and the next minute it might be minus 179 degrees because the transform is moving as part of the animation. So I think we probably will have solved this problem by adding that timer. But if not, we'll have to do some kind of threshold that just makes sure that if the angle between Zombie Jill and her target is close to 180 degrees, maybe larger than 170 or something, then we won't bother changing direction based on that. And that will solve it. But I think our timer will probably solve the problem. But hopefully you can see what I mean. As a transform is moving around, if we had a threat here, then it would actually be passing into both of the half spaces of Zombie Jill. So it would be on the left side, then on the right side, on the left side, on the right side. And she would get stuck in a very similar pattern of trying to correct to the left and then trying to correct to the right. So we just need to be mindful that Jill's transform is also being animated when we design these systems. Okay guys, so I think that is pretty much everything done for this lesson. And what a lesson it's been. It's been quite a tough one, especially for me, finding all of these mistakes and design flaws and then having to tell you all about them and of course making myself look like an utter knobhead in public. But don't worry, this is all part of the development process. And in the next lesson, I'm not quite sure what we're going to do yet. I have a few options, so I'm going to think about it between now and then. We'll either work on bringing the player controller into the scene. Now that's just going to be a very simple mock-up of the player controller, nothing too technical, just so that we have something in the scene that we can use like the player camera that our zombie can attack. Or we may go a little bit lighter in the next lesson and just work on our zombie feeding state, that will see our zombie running towards a food threat and then activating its cinematic layer in its animator and watching this zombie go down onto all fours and feast. So I haven't decided yet, but it'll be one of those things, and I'll see you then. Thanks for listening, guys. Bye-bye.